Thanks for helping us review logical operators. And so you might have had to deal with some logical operators on the variables and conditional logic exercise, specifically the rock, paper, scissors, like teaser in there. And so let's talk about that exercise in a little more detail though. In this exercise, essentially, we are asked to convert some kind of written passage, some kind of concepts into code. And so hopefully this wasn't too hard, but basically we are told that the International Space Station sends back temperature readings. And the one that it sent back most recently was -270 degrees Celsius. But we live in America, so what kind of temperature is that? Sure, it's probably cold, but let's convert it to Fahrenheit. And there's some kind of formula, and I gave you the formula here if you click through on this link.
Yeah, so I set the x variable, the Celsius temperature, and then set the Celsius temperature, so it kind of shows which one is which.
Yep, first let's just execute that cell. All right, so starting by just printing what that original temperature is, and here you're just storing that in a variable. Awesome. All right, so now that we have X as our Celsius variable, now you want to talk to us about this next one?
Yeah, so I set Y as the variable of X, and then the equation for and spell Fahrenheit wrong.
Yeah, I do too. It's all good, all good. No worries, no worries.
But then I set Fahrenheit that Y is the thing.
Yep. So here we're doing some math using some variable that was defined earlier. As long as this variable X has been defined some time before and it's in the Colab notebook's memory, after running this first cell, now we have access to X in that variable. So afterwards, we could either below in the same cell or in the next cell start to use X. That's how we would convert any Celsius temperature to Fahrenheit. Cool. So it's using this equation. Awesome. Thanks. We're performing an operation here. We're transforming some variable. If we now get multiple temperature readings back from the International Space Station, like if we also have temperature A equals -250, temperature B equals like -260, temperature C equals like -200. This operation for temperature conversion that we did earlier, I guess we'll have to repeat it 3 different times. And so that might be possible and not that bad, especially if the operation that we're performing here isn't that complex. However, by repeating this multiple times, like print temp A times this plus 32, temp B is times this plus 32, temp C. We're starting to duplicate ourselves here. We're using the same code over and over again. Does anyone see a potential issue with doing this? Using the same code that does the same thing, repeating it over and over and over again. Yeah, it starts to get kind of messy. And we have to copy and paste it each time. That introduces some opportunity for manual error. Maybe the next time we go to do this, maybe we forget or we fat finger it and we do plus 35 instead. And if we're doing this like 100 times, that's an opportunity for some manual error. But also, if this were a multi-line operation, whoa, now our code cell is really starting to get out of hand. So there needs to be some way for us to be able to encapsulate this same logic that we're using in 3 different places in a standalone function. If we move this logic into a standalone reusable function, then the next time we want to update this code, we'll only have to update it in one place inside the function. In other words, if, for example, the temperature equation were to change, not that in this example it would for temperature conversion, Fahrenheit and Celsius, but if we want to do something differently in the future, like if we wanted to add 35 instead of 32, if we're repeating ourselves, now we have to change the code in 3 different places. And so that might open up opportunities for manual error as well. Maybe we forget to change one of these places. And so now there's a divergence between us trying to perform the same operation, but messing it up. So anyway, that's why if we want to do this operation over and over again, we might encapsulate this shared logic. Take some temperature, multiply it by this, and then add 32. We can encapsulate that inside a reusable function, and then we'll just reuse that same function. So this is where we're going today with our functions exercise. Why don't we encapsulate this shared logic in the same place? So we'll define a new function using the def keyword. Now we get to choose a name for this function. Let's call this one maybe like convert temp. And when we create our own function, it takes a number of parameters. Whatever parameters are applicable for the operation we need to do. So maybe we'll come back to the parameter in a sec. Just like an if statement, we need a colon, enter, and an indent. And now we'll need to return some kind of version, some kind of resulting value here. So when we're dealing with a function, we get to choose what our parameter name should be called. So we're going to pass probably like a Celsius temperature in here. So I might call this parameter C, for example. And whatever Celsius temperature we pass in, now the inside of the scope of this function will use that value, consider it to be a variable called C, only because that's what we chose here inside the parentheses in this function definition. Whatever temperature we pass in, it's going to get multiplied and added, and then the result will be return. When a function returns something, that means that we can store it for later. What I mean by this is the following. Now we could say something like convert temperature of temperature A and we could do this for all of our different temperatures. And so now we are starting to clean up our code and not repeat ourselves. And so this works the same way. Just as a quick recap, we'll get into functions in a little more detail throughout the course of this class today. But last class, we talked about data types, and they're the objects. They're like the nouns, the building blocks. And so like temperature equals 250. That's an object for us to work on. It's like a noun. We could describe it as a noun, like temperature. And that's why you see me starting to use variable names to describe the values. But when we're working with functions, we're performing some operation. It's like some kind of verb is happening. So that's why we'll tend to name our functions verbs. And so the name of this function, I called it convert temperature. We're doing something. A function's job is to at least do something. It could print some messages. It could perform some operation and print the results. A function doesn't need to return a value, but a function could return a value. A function can return only one value, and the return needs to happen at the end. So just another example of why functions are helpful is that they help us simplify our code. To remove duplication, there's a principle in software development that we want to adhere to called DRY. Do not repeat yourself. So here up in the first example, we were repeating ourselves a lot, times 1.8 plus 32 over again. That introduces opportunities for manual error. and also starts to get not the most readable, especially if this operation takes multiple lines. So instead, we performed a task called refactoring, or reorganizing the code. It still does the same thing, but now we encapsulated this logic in a standalone function that we can invoke or call over and over and over again. And you see us doing that here. The return value allows us to do something like this. Result equals convert temp. And now, oops, convert temp. And we'll pass in some value, maybe like 60. Whether we store that in a variable first or not. In these first three examples, we were storing these temperatures in their own variables, and that's all good. We were passing the variable in to the function as a parameter. Once the value gets passed in, the function treats that value as whatever parameter we defined, in this case, C. So it'll be like, all right, temperature, multiply, and then add, and then finally return that. And that's why we see something printed at all. And that's why we can then store the result in a variable and then print that. Like the result is the following. Just using some comma separated print statement here. It's the return that allows this kind of thing to happen. After we invoke this function, we're going to get back whatever is returned, and then we can store that in a variable for later. I just want to pause and see if there's any questions about what we've done so far with functions. A little ad hoc function definition here. All right. So why do we use functions? Well, it helps us not repeat ourselves. We can take some logic that's shared and just stick it inside of a single place and then invoke that same function over and over again. So it's good for code maintainability and also helpful for readability. And finally, now we have an opportunity to verify whether or not this function is working as expected. So this next concept is a little advanced, and we'll do more of this if you take my OPIM 244 class in the fall, when we focus a lot more on quality control and refactoring. Since we now have encapsulated this logic into a function that we can invoke with different inputs and see how that function returns different outputs, there's some tests that we'll need to do to see if our function is working as expected. So like, maybe we could choose an example temperature in Celsius and see if it comes out as the expected Fahrenheit temperature that we expect. This is like an advanced thing. If you want to include some of what we're about to do in your deliverables, I would love it, but you don't need to feel obligated to do this. It's called unit testing. For any function, we can just invoke it, pass certain parameter values in, and expect that we should receive certain resulting values out. So if we wanted to test this function, we're asking like, does this function really work the way we expect? Or is there a bug in here? I think it's easy for me to know that, like, in terms of Fahrenheit Celsius equivalents, that if we were to pass in, I think Celsius temperature 0, is that Fahrenheit temperature 32? So we would expect to see 32 back. Let's just invoke this real quick. Convert temperature Celsius 0. All right, we get 32 back. That's awesome. And so now visually, we just did a test. Does our function work the way we expect? Here's one edge case. If the Celsius temperature is 0, what do we expect to come back? 32? All right, great. Visually, we've just tested this function. But to be explicit about this, we'll use a keyword called assert. And so what we could say is something like this. We'll assert that when we invoke this function and pass in a certain parameter value, that the result should be equal to, in this case, 32. And so I'm just going to print, hey, we got to the bottom afterwards. The assert keyword, if everything is going right, you won't hear from it. It won't complain. If this cell gets to the bottom without error, then our test is satisfied. It was the case that when we converted temperature 0, that the resulting value is equal to 32. The same thing goes if we were to store this in a value as well, like result equals convert temperature, I don't know, maybe like 100 this time. And then we could assert the result is equal to, I don't know, what do we expect? I forget, let's print it out first. Oops. So when you're testing, here we see 212, and if that matches our expectations, just to codify this, we might do something like that. So in both of these instances, we're using the assert keyword. Maybe we're trying different edge cases, like does the function work with 0? Does it work with 100? Does it work with negative values? What if we mess up? What if we were to pass a string in there? That's the kind of thing we're getting into when we test our function using this assert keyword. If we were to have asserted something that's false, like assert 2 plus 2 is equal to 10, then the assert keyword will yell at us. So this is what's happening when we're using the assert keyword. It's like, if our expectation is met, it won't complain. But if the expectation is not met, then it will complain and it will throw an error. And so this is the way that we can explicitly test whether our functions are doing what we think. So I'll be adding a bonus challenge perhaps to your rock, paper, scissors exercise. I haven't added it, and I'll be asking you to perhaps try some testing for bonus. And so all we need to do is assert that when we invoke a function passing in a certain parameter value, that we will get a result back that matches our expectation. Yeah, question?
Will this only happen if you know the expected value?
Yeah, you have to know what your function is supposed to do. That's why you see, like, we would otherwise do some math, find out the expected value, and then just codify that expectation there. Yeah. Other question? Yeah.
So that word is supposed to do it.
Right. It just either complains or not. Yeah. All right. That was an intermediate topic. So if you're like, whoa, testing, can we just focus on functions? Yeah, let's just focus on functions now for the remaining few minutes.